So this is the AP content. Don't get me wrong, we've covered AP content already, but this is just the not at all even in the Alberta curriculum now, fully just AP content. Okay, so if you are in Physics 20 AP in Alberta, this is going to be on the AP test. Everything else we cover in Physics 20 will be as well, but of course this isn't material that is on any other of your in-class tests or finals, okay? So what are we going to talk about? Well, we're going to talk a little bit more about circular motion, but now we're going to start calling it rotational motion. So we already talked a lot about circular motion, right? We talked about it in the situation where position was always, of a particle was always a radius away. I don't know why my PowerPoint has done this. This is supposed to be just a vector symbol on top of those. I don't know how it became ours, but again, PowerPoint on the iPad sometimes just starts forgetting things. That should also say equals. So there we go. So the radius was always constant, and of course we only talked about when a particle was moving at a constant speed around in a circle. And that's what gives us the uniform part of uniform circular motion. And of course, we know that a period was one time for, the time required for one complete rotation. And so then we were able to say that since the speed around the circle was a circumference divided by the period, then that's equal to 2 pi r. Again, wow, it's leaving out lots of stuff here, divided by the period. So for that particle in circular motion, uniform circular motion, the velocity vector was constant, but of course it's continually changing direction, and that is where acceleration comes from. That's where centripetal acceleration comes from. Centripetal acceleration doesn't tell us about something that's speeding up or slowing down. It's telling us about something that's constantly changing its direction towards the center of the circle. Okay, so that is circular motion, and we did a whole unit on that. But what we're going to start talking about is rotational motion, because really there's so much more to things moving in a circle that we need to be able to describe. Okay, so that's what we're going to look at, because this is still just looking at our tangential velocities, everything going in a straight line, right? We're trying to take something moving in a circle and still break it down to straight lines. Now, what if I don't want to actually do that? What if I actually want to look at how it's moving circularly? So how we're going to start that is by talking about angular position. Okay, so basically how much is its angle changing, or what's its angle change with respect to time? Well, that's going to get into speed, but we'll just talk about angular position. So usually you guys measure angles in degrees, but if you've taken Math 30 already, you'll start to see angles being measured in radians more often. And that is just a whole new unit for you. So before we even get into anything else, we need to figure out what the heck radians are. Okay, so again, we're always going to use theta now. But instead of using degrees, now we're going to start using something like radians. So we can see this angle right here would be about, 30 or so degrees. So I want to know, what is that in this new unit called radians? And you're going, what the heck is a radian? Well, a radian is the angle subtended by an arc whose length is equal to the radius, blah, 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 blah. What the heck does that mean? Basically, the radius, it goes from the center of the circle to the edge of the circle, yes? Here's the radius. Here's a radius. So if I take that length and then I follow that length, but I put it around a circle, okay, that would be a radian. If these two blue lengths are exactly the same, that would be 1 radian, okay? So that's what a radian is. It's basically the length of the circle, the length of the radius, take that, detach it, and make that length along the arc length of the circle, or along the arc, like basically curve it, okay? And that's what a radian is. So I know this is like all the nice fancy language up here, but that's basically what it's saying. Angle subtended by an arc, okay? This is the angle, this is the arc, right here, whose length is equal to the radius, okay? So this here, if this length is the same as the radius, that would then be 1 radian, okay? And that's what a radian is. A radian is equal to 1 radius, okay? So there we go, we got R right there, we got R right there, so those are both radiuses, but when you put it along the arc of the circle, that is 1 radian, okay? And so of course a complete circle is 360 degrees, but we need to know what is that in terms of radians. Well, we have a lot of things. We have something really, really important. It's like a really important number that's literally defined by how many radiuses fit around a circle, and it's of course pi, right? How do you get the circumference of a circle? That would be a full 360-degree turn. Well, that is 2 pi, right? So there's 2 pi radians in 360 degrees. Okay, so if you were to take this and go all the way around, that's 360 degrees, of course. But how many radians did we subtend all the way around here in order to get those 360 degrees? Well, 2 pi, because that's how many radiuses are in a circumference. Okay, so I know it's a lot to sort of try and wrap your head around right now. It's something that you'll get much, much better at as we keep going. So, and then the good news is you're going to have a bit of a jump on Math 30 because you're already going to know what a radian is. Okay, so think about it this way. Again, here's our full circle. So of course, here's my radius. Let's draw a radius from the middle to the outside. And so 1 full turn from that original line, that guy right there, theta, that would be 2 pi. Because we know that a full turn around a circle is a 2 pi turn because that's how many radiuses we'd fit in, right? Because really, if you look at it, if this is the radius r, then that's about a radius r1. There, it's another radius r. There's 2 radians. There's 3 radians. So, oh, look at that. A little bit over 3 would be a half circle. A little bit over 3. Where does that come from? And you keep going like that. So it would be another radian, another one. So we're at 6, and then we have a little bit extra there. It's probably a little bit too much extra because I was doing a very rough draw of it, but that is a little bit over 6 radiuses. Oh, it's 2 pi. 2 times 3.14 is 6.28. Oh, so there we go. Hopefully it's all coming together. So that's how we know that 2 pi radians is 1 full circle. Okay? So we're just saying how far around the outside is it, and that's what we're using to show us what our angle is. Okay, so it's how many radiuses around. So this would be the same as 360 degrees. Okay, so here's a question. How many radians then are going to be in half of a circle or half a turn? Right, so we think of that as a 180 degree turn. So say I'm going to do a 180. What does that mean? It means you're doing a full half turn. Okay, so we know that this theta right here is 180 degrees. But what would that be in radians? Well, if a full turn around the circle is 2 pi, then half of a turn around the circle would be just 1 pi. Okay, so that's just pi. We don't even have to say 1 pi. That would just be pi. Okay, so pi radians is half a circle or half a turn. Okay, and then you can kind of keep on going from here. Right, so say we wanted to do a quarter of a turn. Well, again, usually we know that as 90 degrees, right? So say we start here, And then we do a quarter of a turn and we're up here. 90 degrees, always very, very important. So what if this is my angle? Well, we know that's 90 degrees, but I want it in terms of radians. Again, I know a full circle, a full 360 is 2 pi. I know a half of a turn is pi. So really, this is a quarter of a turn. So it's a quarter of 2 pi, which is just pi over 2, or half of a pi, right? Because again, we know pi is a half turn, so a quarter turn is half of that. Okay, and then you can kind of keep going from here and do a bunch of different turns. We'll just do one more here. So what if I had 3/4 of a turn, which is usually a 270 degree angle. Okay, so what if I had that? Well, that is a full pi and then another half of a pi. So that would be 3.5 pies, right? Because we know a quarter of a turn is a half a pi. So that's really like 3/4 of a turn. So it's 3 halves. There we go. And then you can kind of extrapolate from there. You can find in terms of radians, in terms of pi for like 30-degree angles, 60-degree angles, all that fun stuff. But thankfully, of course, in physics, we often want just numbers. We don't want 2 pi or 3 pi over 2 or whatever. We actually want the value to a certain number of significant digits. So that's the good news, is knowing all the different angles in terms of pi is something you can save for Math 30 here. Okay, so now that we know what radians are, and that's actually going to be sort of, it's going to sub in for our distance now. Okay, we want to know how many radians, how many lengths around the circle are we doing. And by the way, we can find the radians of how many turns something is doing by taking the length that it goes. Okay, so if this wheel is turning, I want to say, okay, how far did the wheel end up going down the street? And I divide that by its radius, it's going to give me how many turns it had, okay, in terms of radians. And that's what I need to know. Okay, and then of course we can use that to go on to angular velocity. So basically we kind of just did angular displacement. That's what pi is. That's kind of its tie to what we've known so far. And then of course we can go into velocity and angular velocity. Because what is angular velocity? Well, just like regular velocity, linear velocity is change in distance over time. Angular velocity is change in angular distance over time, right? It's the change in how many rotations it's done divided by how much time has passed, okay? So here's, by the way, a new letter that you've probably never seen. You're like, is that just a really weird looking W? It is not. It's a Greek letter. It's called omega. Okay, well, that's a weird drawing of it, which will happen, but let's try to draw it as nice as possible right now. Okay, so it's kind of like a really loopy W. It's called an omega. Okay, and we use it for angular velocity. So it's not a W. That's like half the reason. No, that's probably like the whole reason why I do pointy W's and not loopy W's, because they look so much cuter, but I don't want it to look like an omega. So there you go. How taking math and physics for a long time changes your life in the ways you never thought. So there we go. Omega, av, that's just average angular velocity, is equal to the change in angular displacement over time. And that mirrors the equation that we already know and love, v equals d over t. But again, that's just for linear transitional velocity, and now we're talking about angular velocity. Okay, so that's a nice, useful sort of equation. So again, I look at the angular displacement, it all's going to depend on what the angular displacement is, your angular velocity. Okay, but then again, depending on what you have here and how far you're going and how long it is, it might be the same. But basically, just remember that it's always change in angular displacement. So we always want to use this as our reference line. Okay, if I were to draw a Cartesian plane right over this, what would this be? This would be the positive x-axis, which is where we start everything from, and that's why it's our reference line. So we always go from there, and we go counterclockwise from there. We can go clockwise, but we don't usually go counterclockwise. So if I want the change in angular displacement, but this is its initial position, right? This is the initial angular displacement, and then this is the final, then I need to find the difference here, okay? By taking this radian and, this one and subtracting this one, if that makes sense. So always remember that you always have to either start from the positive x-axis, and if you don't, to find your change in angular displacement, you're always going to have to subtract however far away you are from that reference line, okay? So something we'll deal with when we get to it. Okay, I have a lot more equations to throw at you today, so I know, but, well, this is just going to happen because I'm just introducing a whole new topic to you, and it's definitely a doozy. So, let's relate omega to frequency. What's omega again? Angular velocity. Why would we relate that to frequency? Oh, because anything moving in a circle has a period, meaning how long it takes to do one rotation. Anything with a period has a frequency, which is how many rotations per second or per minute is happening, okay? So we can relate angular velocity frequency in terms of how many revolutions per second are happening, okay? So we know one revolution is 2 pi radians, okay? So therefore, 1 revolution per second is the same as 2 pi radians per second, okay? So if something's moving at 1 revolution per second, but we want that in terms of radians because, of course, we need angular displacement, then that's going to be 2 pi radians per second. And then, of course, if we had 2 revolutions per second, that'd be 2 times 2 pi radians per second. So that'd be 4 pi radians per second, so on and so forth. So that's just really, really important thing to keep in mind. And so therefore, we can also define omega, or our angular velocity, in terms of 2 pi times the frequency, which frequency would be measured in hertz, or revolutions per second, or revolutions per minute, or anything like that. Okay? So yet another equation that you're getting. By the way, these are not on your regular data sheet. You'll be getting a special AP one with all these equations. So let's just do a little example here, okay? So say we have a flywheel on a car engine. It's undergoing a test. Angular position theta of the flywheel is given by 2.0 radians per second cubed times t cubed. So that really just gave you its own little equation for the position of the flywheel. So as long as we have time, we can find the angular position. So we know the diameter of the flywheel is 0.36 meters. Of course, from there, we'd probably want to find the radius because usually that's what we're working with. So that's 0.18 meters. All right, so we want to find the angle theta in radians and degrees at times t equals 2 seconds and t equals 5 seconds. Well, that's going to be pretty easy because they literally gave us the equation. So let's start with that. Let's start with part A. So at 2 seconds, again, it said 2 radians per second cubed times t squared. And of course, this is when it's at 2 seconds. Oh, was it squared or cubed? It was cubed. Oopsie. Okay, so let's cube that. Okay, that gets us 16 radians. Okay, and that's what we usually want. So if you get an answer in radians, keep it in radians. But it did say, give it to me in radians and degrees. And I'm just doing this so I can show you how to convert between the two, because something like 16, you're like, well, what is that in degrees? And since you're so used to thinking of things in terms of degrees, then we're going to talk about that a little bit more. So how do I convert that to degrees? Well, what is a ratio between degrees and radians? Well, if we go all the way back here, I gave you a bunch of ratios. We know that 1 full circle is equal to 2 pi, so 2 pi is equal to 360. We know that pi is equal to 180. We know that pi over 2 is equal to 90. We know 3 pi over 2 is equal to 270. So I gave you a bunch of ratios here, but this is probably the easiest one to use. Okay, so we're basically just going to make 2 ratios equal to each other, because we know for every 180 degrees, I have pi radians. Okay, but I want to know how many degrees, what theta degrees do I have when I have 16 radians, right? Because the ratio should always be the same. Okay, so you're basically just making 2 ratios equal to each other, and then if I want theta here, I just take 180 divided by pi, and I multiply by 16 radians. Okay, and then say I had degrees, but I wanted radians, I just would flip both of these fractions around. Okay, but basically, what do we get for theta 2, but in terms of degrees? 180 divided by pi times 16 gives us, just a sec, don't know why I don't already have this worked out. So 180 divided by pi times 16 is 917 degrees. And I know this one kind of said, you know, should have 2 significant digits, but honestly, I don't really care right now. 2 or 3, I think, 2. But I'm not worried right now. I'm really not worried. Just because I want you to get to know, you know, 917 degrees, what does that look like? So that's going to be, you know, over 2.5 turns for sure, if 1 turn is 360. Okay, so it said do that for both 2 seconds and 5 seconds, so we're also going to do this for 5, so I'm just going to call that theta 5. And again, it was 2 radians per second cubed times the times cubed, which is now 5 seconds, so that is 250 radians. And then if I want to put that in terms of degrees, I'm going to do exactly the same thing. Okay, I'm going to make the same ratio and say, well, I know for every 180 degrees I have pi radians, and now I want to know what the degrees are for every 250 radians. It's going to be a big one. And so the angular displacement at 5 seconds in degrees would be 14,324 degrees. So just remember, every time it does a full turn, it's 360 degrees. So then it just keeps adding on itself. So that's a lot. It's a lot of rotations. Okay, that's A. B, find the distance that the particle on the rim moves during that time interval. So I'm guessing the time interval between 2 and 5 seconds. Okay, we have to go all the way back to this equation for this one. Theta is equal to L over R, because, again, angular displacement does translate to actual translational linear displacement. And that's what we need to know. So L at, for basically, we actually want the length that it goes during that time interval. So I'm guessing from 2 to 5 seconds. So we actually here would want the change in angular displacement. So L should equal to the change in angular displacement times R. So that was the first equation I gave you, and that's how far the tire will actually go. Okay, so if it's on the ground at least. So L delta theta. So of course it went from 16 to 250, so we're going to do 250 minus 16 radians. And then I need to multiply that by the radius. It's a good thing we found that to be 0.18. meters. And so the distance traveled would be 42.12 meters, which we'll just leave it at that right now. I'm not worried too much about significant digits right now because there's so much new information being thrown at you right now. So let's just make sure that we know how to get to these correct answers firstly, and then we will worry about other things later. So that's how far it would go. And then, of course, C says find the average omega, which is angular velocity, in radians per second and in revolutions per minute between 2 seconds and 5 seconds. Okay? And so we know that the average angular velocity is equal to change in displacement over change in time. But of course, this time our displacement is angular displacement. And we know our angular displacement is measured in radians. So pretty easy calculation, actually. What is that? So it's 250 radians minus 16 radians. And this happens between 5 and 2 seconds. So that happens in a time interval of 3 seconds. So you can put 3 seconds, or you can put 5.0 seconds minus 2.0 seconds. I'm not too worried. And there we get 78. Now, what do we get for this one? This is radians per second, of course. So there we go. So we got our answer in radians per second, but we still need to find revolutions per minute. And this is when we're going to go back to our handy dandy unit converting ways. Okay? So basically, we're going to do this again, where instead of radians, I want revolutions. And instead of seconds, I want minutes. Okay? And so you're going to do this so all the units you don't want anymore cancel out, and we're left with revolutions per minute. But now we actually have to fill this in, and this one's a little bit different for you. So remember, for every 1 revolution, we have 2 pi radians. And for every 1 minute, we have 60 seconds. So what are we going to do? We're going to take 78, divide by 2 pi, multiply by 60, and we should get 745 revolutions per minute. Okay? So just remember, 1 revolution is equal to 2 pi radians. Why is that? Because the circumference of a circle is 2 pi r, right? And that's all radian is. It's the length of 1 radius. So that's kind of the biggest thing that you got to remember for that. Okay, so we've talked about angular displacement, angular velocity. Oh, wait, no, we're not ready to talk about angular acceleration yet, but you know it's coming. So just let's talk about the sign of omega. We're always going to consider counterclockwise as positive and clockwise as negative. Why? Well, again, because this is usually your positive x-axis and your positive y, so basically staying in the positive quadrants or going more towards that would be considered positive, which I know is kind of weird, but that's just how it is and how it's always been. So counterclockwise would be positive, but if it's going clockwise, that is negative displacement, okay, or negative velocity. Wait, connection between linear and angular, because there is a connection between the two. So particle located at, distance r from the axis, it is going to move, right, from one place to another. So it'll always have that linear velocity, and the direction will be tangent to the circular path, okay? Now we have an equation for the linear velocity, which again is like another way that we can say it is tangential. So that would be the linear velocity at any point, right? This thing is always going to be moving or wanting to move in a straight line, but something's keeping it in a circle. And again, we went over this a little bit in circular motion. So we can derive this equation really easily because you're going, Okay, there's yet another equation that you're being given. I said there's lots and lots and lots I'm giving you today. But why? Well, first of all, we know velocity is equal to displacement over time. And then as we found out in circular velocity, well, if my displacement is 2 pi times r, that's the circumference, it's going to go over a round of circumference in 1 period. Okay? But we know period. This is kind of the same as saying 2 pi r times 1 divided by the period. What is 1 divided by the period? Oh, that's frequency, isn't it? That guy right there. And so therefore, we have 2 pi r times f. However, a little while ago, I said that 2 pi f was something special. I'm going to go back all the way to here. Oh, look at that. 2 pi f was angular velocity. So therefore, oh, look. 2 pi rf, well, again, we just care about this bit, but that is angular velocity. And so therefore, what do we have? We have r times angular velocity. So there we go. And that's why our tangential speed, so we'll call that vt, how about that? Our tangential speed, or just the linear velocity, is going to equal r times omega, the radius times the angular speed, okay? Because at any point, we can always look at their linear velocity or their angular velocity, because it is technically measuring two different things. Your angular velocity is how much is the angle changing over time, and of course, linear velocity is how much distance you are covering over time, okay? So let's talk about those in relation to each other. So we have a rotating carousel. One child is sitting on a horse near the outer edge, and the other child is seated on a horse halfway from the center. Okay, so outer edge, center. Which one has the greater linear speed? So what I want you to ask yourself is, who's covering more distance over time? Child 1 is. Because even if you just look at this little bit, right, this guy at this point has covered that much. This guy has covered that much distance, which is more distance, right? So child 1, because they're covering more distance over time. Okay, so that will always be true on, if two things are on something that's moving in a circle. Farther you are to the outside, the greater your linear speed. I want to know which one has the greater angular speed. So remember, angular speed is what angle are they displacing over time. And I don't know about you guys, but this looks like the exact same angle this whole time. Right? They're all covering this angle theta, so therefore they have the same angular speed because they're displacing the same angle over time. Okay, so there we go. That is angular displacement and angular velocity and how it's related to linear velocity. And I was jumping ahead earlier to angular acceleration, because if we can get angular displacement, angular velocity, obviously we can also look at angular acceleration, just like displacement, velocity, acceleration are tied together in the linear world. So that's what we're going to go on to next.